All right, ladies and gentlemen, good afternoon. Today we're going to talk a little bit about balancing equations. This goes directly in line with one of the bell work questions that we did in class today. So I just want to reinforce certain concepts and make sure you understand what kind of skills you have to know in order to be able to do your bell work questions and to be able to balance equations. So first, before we even get to balancing equations, we have to make sure that you understand how coefficients and how subscripts work. So for example, we're going to start with something easy, and this is iron oxide. You'll see here it says Fe2O3. So what that means is we have 2 irons and 3 oxygens. So the subscript only relates to the element immediately to the left of the subscript. So this 2 relates to iron and this 3 relates to oxygen. So for every iron oxide molecule that we have, we need to have 2 iron atoms and 3 oxygen atoms. Over here, we have what is called a coefficient. In this case, what this is saying is I have 2 hydrogens. Okay? Now this is very simple here. You could actually also write hydrogen as H2 because it exists as a diatomic molecule. Don't forget that vocabulary word. It actually appears on page 41 in your notebook on the 3rd paragraph. So, but this is just to show you what this means. Now we see again the coefficient, but this time it's in front of a molecule. Why is this important? Well, whereas here the subscripts are related directly to the element to the left of it, this tells us we have 3 molecules of water. So in order to build 3 molecules of water, if we were using our atomic kits, what would we have to do? Well, we would need 3 times 2 is 6 hydrogens, and 3 times 1, remember, the subscript is assumed 1 if there is no subscript there. 3 times 1 is 3 oxygens. Okay? And if you're unsure, you can actually build a molecule. If I'm building 3 water molecules, I need H2O, H2O, excuse me, H2O. By the way, that's kind of what they look like. They look like a chevron. Okay? 1, 2, 3, 4, 5, 6. 1, 2, 3. Okay? So in front of a molecule, which is where you would normally see what a coefficient is placed in front of a molecule, it will tell you how many of the entire molecule you have. Okay? Now, we have something that looks a little scary here. Okay? We have here 1 carbon and here 2 hydrogens. So we have 1 carbon and 2 hydrogens. But then we have a parentheses around this particular molecule OH, and it's got a 4 next to it. Well, this kind of works like a coefficient, except it's not applying to the entire molecule. It is only applying to this portion of the molecule. So what this is saying, this particular substance, which is ethylene glycol, it has 4 hydroxide subgroups within the molecule. So how do we make that? Well, you have OH, 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 and OH. So how many oxygens do we have? 1, 2, 3, 4. How many hydrogens do we have? 1, 2, 3, 4. If you were to do the math, 4 times 1 is 4 hydrogens. 4 times 1 is 4 oxygens. It's pretty much what I got here, just building it out. So if you want to double check your work, make sure you've got it right. That's one way to do it. But that is how a subscript next to a molecule with a parentheses works. It is you have that entire molecule, you have whatever the subscript number is of it. So you would have to multiply that subscript out by every single element in that molecule. Last but not least, we have a coefficient and subscript combination. I made it a little bit more complicated this time. So here I have carbon, hydrogen, and oxygen, and this is the glucose molecule. So for glucose molecules, I have 4 of these. In order to build it, I would need 4 times 6 is 24 carbons. 4 times 12 is 48 hydrogens, and 4 times 6 is 24 oxygens. Okay? So to find out how much of each individual element you have, you multiply the coefficient by the subscript of that element. And don't forget, if the subscript is 1, or if the subscript is non-existent, it is assumed to be 1. Okay, we just don't write a 1 in the formula. We leave it, for example, here, we don't put a 1 here, it's just H2O. Okay, so now let's talk a little bit about balancing equations. Now this particular formula here, this is the photosynthesis formula. Now I'm going to go through the photosynthesis formula, but I will tell you this formula is not balanced. None of these equations are balanced. I wanted to go ahead and put them unbalanced and show you how to balance them together. Okay? So, in order to do this, what you have to do is make sure that the number of elements going into the chemical reaction is equal to the number of elements coming out of the chemical reaction. Okay, law of conservation of matter states matter cannot be created or destroyed. It is converted from one form to another. Because it is converted from one form to another, everything that goes in must come out. Think about baking a cake, okay? Sometimes you will be asked to bake more than one cake. So if you are baking a cake and you have to maybe bake 2 cakes, what do you do to the ingredients? Well, you double the number of ingredients. If you need 3 eggs for 1, you need 6 for 2. If you need a 1/4 cup of oil for 1, you need a 1/2 cup for 2, so on and so forth. It is the exact same thing with these formulas, but it can get a little bit complex when you start looking at coefficients and subscripts and things like that. So let's take a look. We know that in order to make, for plants, glucose, which is what they consume for energy, and oxygen, which they release into the environment, they require carbon dioxide and water. Okay? So, this is not balanced. What that tells me, if you look here, I have 1 carbon here, but I've got 6 carbons here. That doesn't make any sense. How did I put 1 in but get 6 out? Okay? I've got 2 oxygens here plus 1 is 3, but I've got 8 oxygens over here. So how are we going to balance this formula? Well, let's start with the easy one, okay? The only element that appears once on this side of this equation is carbon. So let's start with carbon, okay? The product here, I have 6. So how do I get 6 carbons here? Well, the easiest way is to add a 6. Why? There is no subscript here, so it is assumed to be 1. So 6 times 1 is 6. So this carbon is now balanced with this carbon here, but we're nowhere near done. So now I have 6 times 2 is 12 oxygens, okay? Plus 1 over here is 13. Clearly, I'm not done yet, okay? So let's take a look at hydrogen, okay? Hydrogen only appears here, it does not appear here. So I have 2 hydrogens here, but I have 12 over here. So how do I get 12? Well, 6 times 2 is 12. Now, I really have a crazy number for my oxygen, right? Here I have 6 times 2, so I have 6 carbons here, and I have 12 oxygens. I have 12 hydrogens and 6 oxygens. Over here, I have 6 carbons, sorry about that. Let's keep some continuity. 6 carbons, I have 12 hydrogens, and I have 6 oxygens. And then over here I have 2 oxygens, so 6 plus 2 is 8. Okay, so clearly my numbers are still a little bit off because although my carbons are balanced, my hydrogens are balanced, my oxygens still are not balanced. Here I have 12 plus 6, so 18 oxygens total on this side. But on this side I have 6 plus 2 is 8. So what do I have to do? Well, if I say I have 6 here and I need to get to 18, what do I need to get over here? Well, 6 plus 12 is 18. If I need 18, that means I need 6 here because 6 times 2 is now 12 oxygens. So 6 plus 12 is 18 oxygens total. Okay, so 18 and 18 oxygens, 6 and 6 carbons, 12 and 12 hydrogens. My equation is now balanced. Okay, so let me give you a little bit of an easier one. It's a little bit easier, but you have to play around with it a little bit. Let's look at iron oxide. You actually saw this on one of your questions, okay? I need iron and oxygen to make iron oxide or rust. We don't want to make rust, but this is how the chemical reaction works. So I can already see something weird here because this is 2 here and this is 3 here. Well, clearly we're not going to be able to splice to go from 2 to 3. So I can already tell you I'm going to need a larger number here. So let me just play around with it a little bit and I'm going to put a 2. And I'm going to see if a 2 works. So if I'm making 2 iron oxide molecules, 2 times 3 is 6. So I would need 6 oxygen. So 3 times 2 is 6. I would put a 3 here. 3 times 2, this is 6 oxygen. Here, this is 6 oxygen. Okay? 2 times 2 is 4 iron. Okay? Here, I would need 4 iron. 4 iron and 6 oxygen would give you iron oxide. Okay? So, hopefully that helps a little bit with balancing equations. We can do a couple more problems in class, but for the most part, this is what you have to do. Once you balance your equations, you're able to identify what kind of numbers you're looking at. For example, one of the questions that we talked about in class would be how to identify moles. So let's say we have, and I'm going to do this with this problem. Let's say we have 4 irons and 3 oxygens. And we're making 2 iron oxides. What if instead of 4 irons, we have 6? How many iron oxide molecules can we make? How many moles of iron oxide? Well, first of all, when they say moles in this context, I have 4 moles of iron oxide. I've changed it from 4 to 6. So this is 6 moles of iron oxide. Well, if I have 6, that means in order to get 6 here, 2 times 3 is 6. So I have 6 iron here and 6 iron here. But now my oxygens are unbalanced because I have 3 times 3 is 9 oxygen here, but over here I only have 6. So my oxygens are unbalanced. So clearly I'm going to have to change things a little bit. And we can see with 6 moles of iron oxide, we won't actually be able to make an even amount of iron, 6 moles of iron, excuse me, we won't be able to make an even number and balance this equation unless we have a fractional amount of O2 molecules. So this would actually come out to something like it would come out to a decimal. So we don't want to do that. So let's go ahead and change this to 8. So if we have 8, well, let's go ahead and balance it. 8 irons here, 4 times 2 is 8 irons here. This also gives us 12 oxygens here. We would actually need 6 oxygens here. So this is 8, and this is 12. This is 8, and this is 12. And we've now balanced our formula again. So if we double the number of iron oxides, the number of iron atoms that we used, we would then double the number of oxygen as well, and it would actually give us 4 moles of iron oxide. So I hope balancing helps. You can play around and go back and forth. You do have to make sure at the end of the process that your numbers match on both sides of the equation. So you have hydrogen, hydrogen, and then 18 total oxygens here and 18 total oxygens here. So make sure you're adding up all of your individual elements. I hope this was helpful. If you have a question, please do not hesitate to drop a comment. I'll be happy to answer, or maybe make something else as an addendum to this to kind of help you understand how to balance your equations. Have an awesome night, and I'll see you tomorrow.